hash too much about talk about specific with Solaris, because there are some pretty big differences between the way these kind of ring system works, like FreeBSD or Solaris. So why are we doing the talk together? I'm Job, by the way, we can go back to the previous sheet. So my name is Job. I did a kernel module for Solaris about 2 years ago, 1.5 years ago. I did we talked about it last year. Conrad also did work on kernel modules. We did also some work in hiding stuff, but also some stuff in against these techniques. And so now we're jointly presenting this work. This is the overview. First, an introduction on the Solaris specifics, then some black hat issues that you can think of and that were implemented, and then some white hat issues, because they're also pretty useful uses for kernel modules that people might not mention, but it is. So how are we going to do this? First, Conrad is going to give the introduction on the Solaris part. Then I'm going to do the black hat issues, and then Conrad the white hat issues. It doesn't mean that I only programmed that part, because a big part of the black hat issues is also Conrad's work, but we will be commenting on each other's work while we speak. So, Conrad.
Okay, I'm turning the microphone that way. It looks cool.
Oh, whatever you want.
Okay. Yeah. So I'm going to start with an introduction to the architecture of Solaris and the important point. If you work with Linux kernel modules or FreeBSD, you know a lot of things about that, but there are some differences. The question we should answer: why the heck deal with Solaris? It's a commercial system, and some people don't like that. And it's sort of not that free. I'm going to later talk about the source license of Solaris. Solaris has some advantages. It uses POSIX system calls, so porting stuff is simple, or should be simple at least. Then it's a System 5 theory based. You have all the comments you know, like LS or whatever. And it's also using 64-bit with the UltraSpark architecture, and it's running fast, even with SMP support. And on the other hand, Solaris is used often in big systems, in enterprise systems like banking, e-commerce. It's a common platform for professional application and services. And that's why we tried doing something with it. And there was not so many public information about how things internally work, how kernel stuff is done, and there was nothing or very few information about how to make bad things or good things in kernel, like black hat or white hat issues. That's the reason for the talk, so that we can get an overview of what can be done and what's the difference to other prior works that did the same thing with Linux or FreeBSD or OpenBSD, whatever. So the kernel itself is a monolithic kernel. As with most common operating systems, it's all in one bit. The functions, the kernel functions, the complete stuff is in one big binary file. It's not something like BOS where it's a microkernel and it's divided. It's the big mess. Andrew Tanenbaum, the famous author and one of the biggest enemies of Linux Torvalds, called this the big mess. And that's also the reason why the Linux kernel is bad in his eyes. But I guess it's okay. Solaris also uses modules to achieve a dynamic kernel functionality, to unload and load functionality where necessary. And the important point that you have to care when programming in the kernel is the multi-threading. Some people say that the Linux kernels or BSD kernels are multi-threaded, but there are only few kernel threads running. There are only 4, I'm not sure, maybe 3. On Solaris you have several threads, and they are always running, even if you're using a non-SMP machine. Maybe you bought some cheap computer, installed Solaris, and then you think everything is done. There are a lot of threads working in the kernel, and you have to protect your code and ensure that there are no two threads accessing the same data. I'm going on to this later. So this is the concurrent programming technique you need to develop stuff, and this is probably the most difficult part of it, especially if you port something from FreeBSD or whatever to Solaris. And the architecture itself, it's modular. You can easily do many things. Of course, you can load modules. You can do this dynamic, or if you open the device, the module gets loaded. This is very similar to other Unix systems. And you have a wide range of possibilities to change things inside the kernel. You can use the switch tables. You have linked lists. Most linked lists in Solaris are cyclic lists, so you have a little bit to care about this. There's no head and tail for the list. They are linked like a cycle, and you have to assure that you're coming back at the end, so that you keep the list constant if you change something. And there's also a lot of string stuff in the Solaris kernel, like with most other Unix systems. Yeah, that's the next slide. Okay, this is a very short overview of a kernel module. There are 3 functions that need to be implemented. It's an init function which starts the loading stuff of the module. This is also the place where you have to start. I'm going later to this, but I have to say this now. You have to start the concurrent programming parts. You have to start the logging at this point before the module is loaded. And yeah, therefore this is very useful that you can set the mod install instruction after you have started logging the resources. Then there's an info function that returns information about the loaded module, and finally there's a finite function that removes the module. And in this place you probably want to check if some of the resources you log, or imagine it's a device and somebody is accessing the device. This is a place to check if it's really possible to unload the module. Well, if somebody is viewing a video on your device and you have the module loaded, you cannot simply unload it. So we've heard about this on FreeBSD. I guess it's simply the very same thing. It's even called the same name. It's a sys entry table for system calls. It works just the same as explained. I'm not sure if there's a flag like this. There's an argument flag in the syscall table. It's not pointing to the syscall table. It's not pointing to the syscalls directly. There's a struct between the complete thing. And if you're adding or modifying syscalls, you have also to care for other values, not only the jumper, the address you're jumping to, but also the arguments of the syscall. So you can change it if you're implementing a new syscall and it has 4 arguments. You have to set the SYNARE value to the proper value. So yeah, and there's also other things to care. I already said that you have to deal with concurrency. You also should lock the syscall table when changing it. That's also the difference and problem of the multi-threaded kernel. You have to assure that there's no other process or a kernel thread accessing the syscall table when you add your changes. And you have to use reference counters in all your syscalls. Maybe you trap a syscall and you want to unload your module, and somebody is inside the syscall you change, and you unload it, it will crash. Therefore, you have to keep track of people which are inside the syscall at the moment you're unloading. This is done by reference counters. Like it's a similar concept to Java, which uses the reference counters for garbage collection. So you can say you can collect your unused syscall and then unload them if there is no one accepting them. So now we go to the concurrent part. This is probably a little bit theoretical. It's not that Solaris specific, but it's important for Solaris kernel programming. But you can use all the things I explained now if you're programming threads. And the function names are similar to pthread function names. You will see this later. Yeah, as I said before, the kernel threads execute currently at any point, so there's no way to get a safe state where you can act. You have really to ensure it at any point in your code that you keep the consistency of the thing. And with normal threads, with pthreads, the only thing that a thread really owns is its own stack. So all resources except the stack, like shared memory, devices, open files, this is also shared. They run all the threads working in the kernel. So if you're allocating memory and you write something into that memory, you can not be sure that another thread is not, in that second you write to it, writing also to it. And you have to use locking mechanisms to protect these critical regions. And this is done by using mutual exclusion. This is a concept that was invented some years ago. Dijkstra, who was one of the famous guys I know from the Netherlands, he invented in 1964 the concept of semaphores. They can be used for mutual exclusion, but they can also be used for other things, like sharing resources, if it's something multiple users accessing shared resources. But in this case, we will focus on mutual exclusion. There are two functions that include semaphores. This is the up and in down instruction, or it's also called release or pass. In the Solaris kernel implementation using Unixes, it is called lock and unlock. It's simply like the lock that you get, you log it and you unlock it. The concept behind this is that you have an integer value in your semaphore, and if you do an up, it decrements the value if it's not non-zero or if it's below zero. Whatever. And if it's already zero, then somebody has already accessed this part of the code. And then the thread is blocked. It's put into your queue, FIFO, or whatever, and waits. And when the thread that's inside the semaphore issues a down comment, it awaits waiting threads, and if no thread is waiting, it increments the value of the semaphore. I made a little simple graph of this, so you can see you issue the up comment, and then you are inside the critical region, and you can assure that nobody else is inside this critical region, and then you do the down. And there's no other possibility to enter the critical region. I actually plan to demonstrate this with a graph of two threads accessing one resource, but it was too big to demonstrate. There are a lot of states getting easily done by the program who generates such graphs. And so I choose this symbol. I guess everybody can imagine how this works. So now to a code example how this is done. You see, as I said before, when you load the module, or better, before you load, when you're inside the init function of your module, you initialize your mutex, which is an abstract for the semaphore. You initialize it before loading, then you load the module, so you can be sure that the mutex is working and it's initialized properly. And if you end your module, you unloaded it, then you destroy your mutex. And the code that is critical is just put between a mutex lock and a mutex unlock. This is a clear concept. It should be the same with normal threads and G threads. But you have also be careful when doing this. Mutual exclusion is the root of deadlock. Whenever there are deadlocks, this has something to do with mutual exclusion and using the described techniques. And you have to avoid there are four conditions for deadlock. The first one is mutual exclusion, so I'm not programming it. You cannot avoid using mutual exclusion if you're programming in the kernel. You have to assure that somebody is protecting your area. So you have to try to avoid the other three conditions that cause deadlocks, which is hold and wait. You can imagine if somebody holds a lock and then waits for another lock, then somebody else can never access it. And this is also the circular wait problem. You have, imagine you have three threads accessing a resource or accessing three resources. And one gets the resource and blocks it, the other gets the other, and the last one gets the last resource. They all have one resource and they're probably waiting for the other resources. Each is a circle. And so nobody can access anything. So you have to avoid circular things, and you also have to avoid situations where you don't have the chance to preempt the code. But in the Solaris kernel, there's preemptive threading, and there's no chance that anything can preempt it. You have also to care, if you're using mutual exclusion, about the speed of this mechanism. It's use it only where necessary. Don't block the complete code. This is useless. You would slow down the compression and use different mutual exclusion for different critical regions. Don't use the same. I use this in my security module. That's why I didn't release it to this day. It's the problem is if you're using the same mutual exclusion for all critical regions in your code, it will block at one stage, and if you're implementing several syscalls, it will block all syscalls you change, and this is probably not what you want in your final state. Therefore, use different mutual exclusion mutexes where in independent regions. Yeah. The next thing is, if we are focusing on black hat or white hat issues, whatever, we need to know what actually displays, what gets back from the kernel to the user of the system. This is done by syscalls. They are used to get the resources from whatever hardware, I/O. They get the resources to the user and copy them. This is a place to intercept or change anything. Then there are devices. You can access the devices directly, so you have also a chance to intercept or change anything here. You have the file system, and you have the KMEM device and the MEM device, which represent a pseudo device for the memory in the system and the kernel memory. And the involved structures of these parts are arrays, as with the syscall table, switching tables that hold, for example, the function pointers to file system functions, as the same thing as in FreeBSD, as we saw before. Then you have linked lists of processes. Most Unix use linked lists to keep track of the running processes, of the processes that are waiting, of the processes that are preempted, that are blocked, waiting for a device, whatever. Then you have global variables. They're commonly used for debugging purposes. There's a file called easy system. There you can set some of these variables and modify the working of the kernel, or cause the kernel to give more debug information. Just look at it and you will see it's uncommented, but you can simply remove the uncommented and then you can access this functionality. And there's also a symbol table that allows changing symbols. We saw this before. Yeah, now we're going to the black hat issues, coming to the equal stuff.
Okay, this works. Okay, yeah, so that's the introduction. Black hat issues, okay, like also with the talk that said that there are like a zillion ways to do black hat stuff. The simple stuff, I think this one slide, okay, so this was one slide that was in between, yeah, well, this is what it says, file hiding, process hiding, module hiding, etc., all the same principles. So one of the things that you can also use your module for, except for the hiding, is of course you want to have access to a system, and you want to have access to a system that's not so obvious that you're accessing your backdoor or whatever on such a system. So you want to have some signaling tricks to get your code know that it's you and no one else, and you want to get some more privilege in that system. So this specific backdoor is a backdoor that I think is also part of the kernel intrusion facility, or is it? Yeah. So okay. So and this describes a trick that you can use. I will also describe some other hypothetical tricks that you can play, or some literature that has been described in Frac, for instance, on how to play with the TCP level or IP level on the kernel, in the kernel. So what could be the goals for the TCP backdoor is execute a command depending on certain network activity. And you really don't want to have like hard-coded things in there. Why not? If someone knows that, and typically with backdoors like this, you copy them all over the place, and you don't want to have someone with a really simple check, be able to find the way to check it. So, of course, there needs to be some algorithm hard-coded in there, else, how are you going to figure it? But you don't want to have hard-coded IP, for instance, in it. And you want to have it as suspicious as possible. So this example works in a way that it intercepts the accept call, does normal work, and then it starts listening at or starts retrieving the information that is for this connection. So it can hook on a listening port and then see if there are certain patterns, and there can be any pattern. So in this case, it's a sequence of source ports where you say, okay, if there's a sequence of source ports that's this sequence, then it's my signal. But it can be anything. It can be 5 source ports, or it can be all the same, and the IP ID can be implemented. Or in this case, IP is a little bit less useful because it's not so much in the information you've available at that point. But as Steph also showed, you can hook into lower levels of the IP stack and then process the whole packet, so you can do all the work on the packet. And you want to act on it, and what you want to do is well, most of the time, either you want to spawn something, and in software I wrote in my module that came up there some code that will spawn new processes from the kernel space. So there won't. This is a bit complicated process because normally a process is a fork of an existing process, all derived from the init process, which is the initial process that was started by a kernel, and that's for every kernel. So this piece of coding came up, copied the init spawning part, and it allows you to spawn new processes directly from kernel space without any user stuff. So you can trigger a new process from network activity. So you think of your pattern, what you want it to be, and that can be any coding. You can also use like a spoof source, or do it from different network addresses and do it from different ports, any sequence that happens, to make it as unsuspicious as possible. So what are the advantages of doing this, of course? First, it's hard to detect because typically machines are being used for all kinds of other stuff, so it's seldom that people want boxes that are completely quiet. So the other part is that's implemented in the kernel only, so you don't need too much userland stuff, except of course if you're spawning some process from backdoor, that's yours, but you could also imagine ways to spawn normal applications on the OS that also gives you some additional access. As I said, the source of pieces can be anything. The disadvantage, this is what Conrad found out when he used this module, is that, again, I guess this is, I'm not sure, is this permanent, or can you solve this with your proper concurrent program?
No, you cannot solve this problem. The reason is that if the process is listening on the port, it's calling an accept, and the accept call waits for the incoming page. And if you're in this stage, you cannot alert the module, so you have to wait until the connection is dropped. This may take time, or may never happen.
Yeah, if you're in bad luck and there's like a local connection which happens in Solaris, there are all kinds of demons talking to each other on local host. If any of those connections is hanging, then or live forever, then you can never unload the module anymore. Also, it can be hard to do traffic the pattern matching. I mean, your code that does matching of certain types of ports needs to, have a certain window in where it checks it, or if you don't do that, you might even do accidental, because you can't guarantee that these sequences don't occur normally also. So in high traffic situations, you might get in problems if you don't do it precisely. Okay, so this is some example code of how they can be implemented. you can use a lot of the like library calls in the kernel. The kernel uses a lot of functions for its own utility, and you can use those also in your own code. So in this example, you have the swap name and computer. Another part is the hiding of network information. Hiding of network information like a net stack. So that's also the FreeBSD equivalent. What you have there is in Solaris there are several ways to query this information. So it's not so easy to just take one of those and fix it. A second problem that you have is that all IP or networking stuff in Solaris is streams based, which means it's pretty different from the way FreeBSD works with a switch table, which just has input in input and output routines in there with a simple function pointer. In this case, it's a streams-based architecture is basically a queue where you can have which is messages passing from one queue to the other, and there can be functions that operate on the message. Typically, there's an indicator on the message to indicate what kind of message it is, and you can say, I want to handle this message. Then you can have these modules, streams modules, and they can be stacked on top of each other. So you have normally IP module, but if you want to do TCP/IP, the TCP module is stacked on the IP. So the IP packet comes in and is passed by the IP module to the TCP module, and so it's processed. So and querying about the status of the network is also done through these messages. So a message goes down the queue to the IP module and goes back up to the user application with the queried information. So in this case, there are two implementations, one that Konrad did and one that I did in my module, and they're a little bit different. I'll go over the type that Konrad did and then explain a little bit my differences. The third part, the piggyback thing, is something which is a bit separate from this, but it's a hypothetical thing that you can use also to make it even harder to find modules or network traffic from backdoors. So one of the ways is the get message call. The get message call is the overall call to get messages from any queue, any streams-based queue. So in this case, you analyze if this is a get message for this IP module. And if it is, you check if the size is a multiple of the query reply. The reply is the size of the TCP COM entry. So these are all the connection entries in the TCP module, and that's what gets displayed in the net stack in the end. And as you see, this is not really, how should I say, a robust code. I mean, there could be instances where there are reads of multiple times this entry size, and have nothing to do with the FIP stuff. So, and then you could be looking at garbage and modifying it. So it's a bit of a dangerous thing to do, but it is possible. I've also done in my module some of these checks because it's really hard to know precisely what kind of query reply it is if you're not the application that asks for it. In this case, the IP address that you want to hide is replaced with localhost port, so in effect it doesn't really disappear, but it's changed to a less suspicious value. The port is also changed. So again, all this information comes from the kernel header files, which are in a normal base installed. So if you go in user include somewhere, you'll find all kinds of information on how the Solaris kernel works internally. All the structures that are used are in there. It's a pretty open system, like Konrad said. It's a modular system. That means it's designed for people to use it and extend it and work with it. And if you want to do that, then you need all this information public for the user. So you can see a whole lot of how the kernel works just from looking at a header file, where you also can find this entry. As you see, there's a state field, the local address, the local port, and these fields you can replace. What are advantages of this method? It both hides listening ports and connections for that port if you just check the port or network address. It replaces connections, so it doesn't really hide it, and there are connections there that aren't there, and especially with single connections, if you change them to localhost, all connections localhost are mirrored, so there are always two. And I'll show that in a bit. And the other one is, there's another tool called NDD. And NDD is a bit of a weird tool in Solaris. It's, I don't even know what it stands for. And it allows you to query information in a way that it sends a query to the kernel, and the kernel gives out pre-formatted ASCII text, and all that NDD does is print it on the screen. And in that information is also the netstat table, but in a different format. So if you want to, and there are tools to take the NDD out of the format and just rewrite it to look like a netstat. So you can use a replacement netstat that shows you, and you can also use it as a consistency check of what is NDD telling or what's netstat telling, and that doesn't match. And the problem is it's ASCII, so you have to do, if you have some matching you want to do or hiding you want to do, you have to modify the whole ASCII buffer and search and replace it, which is pretty hairy. It's a real interface, but it's an interesting way to check your kernel. So the new get message looks a bit like this. It checks if you're in the module. Then it checks the size of the data pointer, and then you replace the stuff. And what the effect is that if you're hiding a certain net, you can set a net mask, for instance, then the entry that you want to hide is replaced by the localhost. And you see the example with a normal localhost connection, you have the ports which are mirrored across. They're always a pair, and if you do it this way, then it's not. So what's an alternative? I found when doing the same stuff, and I did it in a bit different way, I hook in the queue for the IP module and catch the information earlier than in this example. So you have a little bit less of overhead because you don't have to be checking in every get message. You only check if you're in the IP queue. The other advantage is the information is a little bit more precise, so I can check a little bit better on the data. And then another thing I found is that if I change the state, which is one of the fields in that struct, to idle, netstat won't show it. So it disappears completely from the netstat output anyway. So of course you can write normal netstat call, and I'm not sure if it's even different from that because there's of course netstat that decides what to print, and the fact that you still can get it from the kernel. But I also zero out with the other entry, so maybe you get an access TCP idle things. So that's an alternative way. So another interesting trick I've been thinking about earlier when I was coding my module is if you want to hide with broken web server, I don't mean that, well, it's broken because you broke into it, but I meant broken into a web server. So you have a web server you broke into, and if you want to hide on such a system, then you want your traffic to it to be precisely the HTTP traffic that goes to a web server and nothing else. So no one is going to spot HTTP traffic in HTTP traffic that's not really HTTP traffic. So what you do is you have your backdoor daemon and you let it listen on a local port. You use the netstat hiding to hide it. And then you can do, because you're in the kernel, and you pretty much can load a complete IP filter into it. IP filter is a kernel module also. But you can also recode it yourself. And you can use the same tricks of catching information, also that step showed that the IP inputs only used on the queue. And then check for access again on TCP port 80 in your local box, but with a pattern matching of like the source ports or whatever, or an IP ID or a timestamp option that's in there. And if that's there, then you can start replacing the destination port to the port of the local port daemon that's listening. So that might be listening on, I don't know, 3333, and then you change port 8 to 333, and everything that's coming back from the port, you code back to 80. So maybe if you get some checksuming or whatever, at least that depends on how much work you want to do on the other end. The effect is that all the traffic going to port 80 with this special flag will in fact go to the other port to your backdoor daemon. If your backdoor daemon is, for instance, HTTP tunnel, which is a tool to tunnel pretty much anything over HTTP, or even better, do it in HTTP gets and posts, then it will completely disappear in the traffic. And you can only find the traffic if you know what the patterns are that are being used to check this module. So it's pretty hard if you do this, and it's not even so difficult because the whole IP filter stuff has been done. It's more like if your module hides properly, then you can just load a complete IP filter with config files and everything and just hide it as fast. Another interesting thing is it was written a little bit about it by Horizon in track 54, where he discussed ideation techniques. And although he didn't really explicitly talk about it in the sense of kernel modules, you can pretty much also easily do it as an extension to these modules. And the idea is that you can, based again on whatever flag, flip any bits in the header. You can flip like SYN flags, or you set some other flags, as long as it's a coding scheme that you know on one end, and do that also on the other end. So you need modified code on both ends. But then when you look at the traffic, and of course you can do full encryption, but if it's just a few flags, it looks like garbage to anyone trying to put together streams or whatever. But in fact, it's just your backward traffic, of course. And I think, well, if you want to do any encryption detection, you should do anomaly detection also, which is hard, but then it will stick out like a focus or tunnel because it's completely garbage going all the way, all the time. Okay, so that's another trick that you can play. And I think that was it for my part.
Okay. Which one? Yeah, that's the right side. So we're now focusing on the positive things we can do with modules. This was also the previous stuff on the very the black hat side of modules. And you can also do really nice things to assist in using modules. You can improve the system security by placing code in the kernel. This is a very secure way. It's not a daemon that is running or any application that is securing the system. It's inside the kernel, so there's less chance that you get beaten out by an attacker. I mean, there's a chance we heard that there's no real security, but it's a good way to protect the system. One approach that I implemented in my security module is a restricted processes. Then I saw this first on the open ball patch by solariskernelfun for Linux. It's a simple concept that shows the process of a user to him and no other processes. So you can only see your own processes, and you don't know what other people are doing on your system. No, the attacker that maybe catch an account by sniffing something, he will only see the process of the user he sniffed and will have less chance breaking the system. On the other hand, you can do try to protect insertion of untrusted code into the kernel. You think like putting stuff into KMRIP or loading modules, even deny loading modules. On most Unix systems, you can simply disable the loading of modules and say, I don't want to have any modules. I simply compile the stuff statically in the kernel, and there's no problem. You can't do this on Solaris. You don't have the source, or you can get it, but then you have no fun with it. you have to have modules in order to have a working system. So I will show some possibilities how to better check for the trusted modules. I guess it's not perfect, and some guys might find ways to bypass this mechanism, but it's an approach. And you can also use the previous things like hiding connections, hiding files, hiding processes as the administrator to hide your tools. You can hide your tripwire tools, you can hide your logs, you can do a lot of things to make them invisible to any attacker. If you would say, okay, there's no admin on this side who's watching the logs, there are no logs, or maybe you can even use fake logs. You can copy the real data to something invisible directory or whatever. And you can also use kernel module techniques for building honeypots, like Linus Spitzer proposed to place a system that attracts hackers, and you log the information. You get more information about what hackers do, how they work, and you get to use the tools. You can also do this as a hacker yourself and get the tools or exploits or whatever. And if you're protecting your system with a kernel module, you have a good chance that the attacker is not able to see that this is a honeypot that he's monitoring. Hiding files, hiding processes, whatever. You need to hide your logging mechanisms so that an attacker is not able to see that you're spying. So to the restricted proc approach. As I said before, it hides the processes of other users. You're only able to see your own processes. And it was the best possibility to implement such thing would be patching the kernel, like it's with Linux. But the Sun source license is very strict, and it's a pain. You cannot publish patches to the kernel. You cannot even public information. What you would add, as I would write something like change line 50, add an A. No information what's in the source. Just say this. This is also restricted by the license. So you have no chance to publish any information you gathered from the source. Maybe it's even illegal that I'm talking here and telling this because I saw the source and they maybe could came to the point that I got this information from the source, even though I didn't do. But so we have to implement a restricted proc as a module. This is not perfect, but it's an approach to handle such systems. So you do this by intercepting the open call. As you know, the process information, most tools read them from the proc file system. You can also read them from the kernel of the default tools like PS or install top or whatever. They read the information from the proc file system. And in order to get the information from this system, the applications open the files that include information about the process. And you catch that open call, and you check. But if they are doing an open, there's a path name, and you check if this path name is lying in the proc file system. If it's in your UF file system or an NFS or whatever, then you just skip it. But if it's inside the proc, then you use special caution. You compare the file owner of this file inside the proc to the process owner. And this is the same concept as with the restricted proc. You can't see other processes, and so you can't open files of processes of other people in the proc. That's exactly the same thing. And if it's happened that somebody is trying to open a process file he doesn't own, then we deny this. I'm using the real UID, it's called in Solaris. It's different to Linux. They have the effective user ID and the normal user ID. On Solaris, I talked to customers like what the real difference is between those two, and it's not really clear. As far as I heard, the real user ID is the one that is the user, even if he's suing or whatever. But it's not that clear how this will develop this real user ID. It's not the same as Linux and effective user ID. And you also have to grant all permission to root so that you can see all processes. Otherwise, it would feel strange system, so root wasn't able to see all processes. So I developed a little struct that holds important information. This is done for. You have a question?
Yes. All your modules go by hiding stuff from too, right? So is there any way to actually hide modules themselves too? Like in Linux, there's very active really
yeah, the same approach can be done in Solaris. You can also remove your module from the linked list of loaded modules and later add it again if you want to make it visible.
Yeah, so doing an dagger or an
yeah. Okay, this track holds only the information about the vnode. This is the thing that if you open the file, you get a vnode that corresponds to an inode or whatever. And I'm just catching information about the attributes and the type of the vnode. And the code is simple. I'm checking if the type of the vnode is vproc, then this file is lying in the proc file system. And the next check is just checking UID against the process UID. You see, I'm using RUID, which is the read UID, which is corresponding to the effective UID of Unix. And if for some reason it's not the same, the file owner is not the same as the process owner, then I just return excess die and just looks good. Then we come to the custom modules approach. This is an experimental. I didn't implement it, and I'm not sure if we'll ever do it. It's a little bit tricky stuff. The idea is to prevent loading untrusted modules. The things we discussed earlier are all based on the fact that you can load a module if you gain root access to the system. And it is important to prevent such stuff happening. Therefore, we're doing the following thing. If we're installing the system, we have a set of modules that should be trusted. At least we believe that on an installation media, the modules are trusted. There are no backdoors in. So we're using a cryptographic system like PGP or UPGP to sign our modules with a secret key that we generated during the installation process. So we need to be sure that during the installation process there's no network connections. The best thing would be to switch the system off the network for installation so that we can be sure that this is the original stuff. And then we sign it and save the sign, the signature to the file. So we have for every module, we have a signature that was generated using our secure key. We need also to protect the secure key. Normally, I believe the keys for PGP or UPG are protected using a password. I'm not sure if it's at the cipher or if it's an asymmetric cipher around the key. I'm not sure how this is done, but both possibilities would fit. Personally, I would prefer putting a symmetric encryption around the secure key so you have another password to encrypt your secret key and then can sign modules. And if you've done this on the installation process and you're finally starting to run the system, what's that slide? Yeah. So you have the signatures of the modules and the modules itself, and you're starting the system, putting it on the network, letting the attackers come or whatever, and you intercept the mod CTL call that is done, which is used for loading, unloading, and other module functions. And if a mod load is issued, you get the signature of the module that it wants to be loaded, and you compare it to the public key. The public key is public, as the name says. If the ICE lays in a directory, you can simply leave it there. There's no protection necessary for this file. So you can easily, from the kernel space, get this file, the public key, and the signature of the module that wants to be loaded, and you can verify if the signature is correct. So far, so good. If an attacker would write an own module, he had to sign it with your secure key. And as I said before, the secure key for your system is encrypted. So there's no chance at this stage to load anything in the kernel that has a valid signature. Yeah?
How do you look long?
Yeah, I'm coming to this later. a smart card or whatever.
Yeah. Why did you say that you don't have to protect the public key? I don't understand that. Because somebody uses its own key here and would replace the public key because you don't protect it. Signature should actually match.
Yeah, you're right. Yeah, this is correct. You could replace. Yeah. So this is correct. You probably need to protect your public key too. But in that case, the real modules wouldn't load. The system might be broke, but it might be a possibility to gain access, and then you could probably switch the mechanism off. So you have to protect your public key.
In fact, the public key needs to be as protected as your kernel files, because that's the same level.
Yeah, we're coming to the problem of this approach right now. Oh, here's a cool graph how this thing works. Well, I explained it already. You see there are two modules, X and Y, and we have both signed them with a secret key at installation, or maybe at another stage, but in a secure environment. This is the important part. You sign them when you're really secure. The best thing would be to have secret key and the software for signing on a CD or whatever, an immutable media where there's no possibility to change anything. And as the module wants to be loaded, you validate the signature using a public key. The advantages, the security of the system relies on the cryptographic algorithms. And they are believed to be strong. You could use algorithms that rely on the factoring problem and ones that rely on the discrete logarithm problem. Both are believed to be very hard to solve, at least now. This may change, so it's always a problem if you're using cryptography in systems that if the algorithm is broken, your implementation is also useless. And also faking signatures is similar to breaking the algorithm, so faking signature must be very difficult. The disadvantages, you have the cryptography stuff inside the kernel. At least you have the part that is checking the signature of the public key and the private public key and the signature inside the kernel. So you have to write this stuff in kernel space. And the kernel is there are not many functions for doing things. It's a very plain area. You don't have libc stuff, and therefore doing cryptography in the kernel might be hard. And you don't have any math stuff. You probably have to implement modulus functions and exponential functions to do this. And the important part that was mentioned by Scott already is that you have to trust the boot path to do this. If anything is untrusted during booting the machine, and the intruder might change the files that are booting, for example the RC files, and then do something, boot another kernel, reboot, whatever. So you have to ensure that this stuff is immutable. You should do this inside the kernel module and protect all the areas that are accessed during the boot process. And this is also leading to the next topic. Oh no, there's a code example. Well, it's simple. You see, the mod CDL is issued, and we check if it's mod load, so that somebody wants to load a module, or maybe it's loaded automatically. You locate the signature file for the module and validate the signature. And if it's not the correct signature, you just return permission denied, and the attacker will know that it's hard to get into the system. So the approach of a protected boot path is also known from PST system. It's rather similar to a secure level mechanism, where you have a level that is switching, and the one part is a secure and the other is an insecure part. And it provides the secure environment during the boot process. And it also restricts root access during this phase, and that's also the important point. If an attacker gains access, he will be root fast, at least on the Solaris system, and therefore you have also to protect root from changing something in the system. It's a rather simple system, as I said before. The secure level has only two phases, which is unsecure and secure. There's no fine-grained structure like I allow this, I allow this. It's rather simple and raw. You have this kernel stack for secure level implementation. toggles between the secure and non-secure level, and you can only make the level less secure. You cannot go upward. You have more secure, yeah. Did I say that?
Yeah.
Okay. Yeah, you can only make the system more secure. You cannot make it insecure. Yeah, that would be useless. So if the system has reached the non-secure level, you cannot, even as root, change it back to the secure level. So you cannot. Oh, okay. Yeah, okay, this is why that's like. So, what I want to say, if you, well, I'm mixing it up again. Just keep it. It's correct here, you see. Okay, yeah, well, one part of secure level is also that you have a trusted environment, and therefore it's necessary that the administrator has physical access to the system. That's what mentioned with console access only, so you can be sure that at least the person is near the computer. It's not over the connection is not made through network or whatever it is. Probably physically. Maybe it might be a serial cable that is going through the room, but the administrator should be near to the system. So now we come to the areas that check for these flags behave differently depending on the flag. There's, for example, a file system that could allow, it could deny handling to files during the boot process, during the trusted boot process. It could deny modifications to files, make them immutable during the secure level part, and it could also protect K-man, because we saw in the previous tutorial that you can insert code directly into K-man. Therefore, you have to prevent this at the secure level and make it read-only. You don't allow any loading of modules during this phase, so that nobody is loading the module just in the second you're preparing the system for your trusted module approach. And you don't allow write access to raw devices during this phase, so that nobody doing it from behind, maybe changing something on the file system in the second you're preparing the boot. The result of this system are a trusted boot path, which could be useful as implementing the trusted modules approach, so that you can be sure that there's no chance to break your signature system with public and secret key. And the kernel even protects root from doing evil things. You can be sure that no attacker is able, on the secure part, on the secure level, to change anything of your code. There are also other mechanisms, but they are yours.
Yeah, these are also some examples that are go a little bit further in the same kind of protection that secure level gave earlier. One of the means that you see coming out now more and more is mandatory access control. A little explanation of what it means. If you look at a normal Unix system where you have your files and you have your access permissions, this is called discrete access control, discretionary access control. I'm not really sure. Anyway, what it means is that it's at your discretion, namely the owner of the file determines who gets access and who doesn't. So I can basically give away all my files, which also happens a lot in Unix systems. People don't watch their own permissions and give away access to all the wrong files that they shouldn't. Another system is mandatory access control. In this case, it's not the owner of the file that determines it, or not only the owner, because they're often in combination with the other access controls. But it's also the administrator that can set policies on what access is allowed. So the administrator can create a system where it's even for root, or I don't think this is a good example because it's still in mandatory access control sometimes it's a little difficult. But it's even more complex to set or fine-grained to set specific accesses to specific parts of the system. And examples of those systems are Trusted Solaris, which is a different version from Solaris. Most of the time it's one version later than the normal, so I think now 2.7 is the latest Trusted Solaris version. And it also has some other features with, like labeling, which is allows you to have the objects coming over a network have a different level of trust than original system objects, the working system already, or compartments in the kernel or in the operating system, where crossing boundaries of compartments is hard. The effect of these systems is generally that the administration becomes usually complex, because these systems, let you set everything. It also reminds you of the mainframe systems. You want to run F, which is the way mainframe is also the way to set it. These can become hugely complex, so they need tools